Welcome back, class. We're going to do some additional practice problems here for you to view at home. We are in Chapter 5, and we're dealing with support reactions in 2D and 3D. So we're going to work on this problem right here. A person is exercising, and they are pulling a load of 8 pounds with one arm, as shown. We want to find the force FH down there at the elbow joint, the force on the humerus bone, and the tension developed in the bicep muscle, that's B. That's the darker portion there. And we want to neglect the weight of the man's arm. Again, we're not given the weight of the arm or the mass. We ignore that. We look at all the external loading as being something much greater than the weight of the objects involved. All right, so let's look at this problem. First thing we want to do, obviously, is a free body diagram. I've already started that just for time. I have this being the sort of forearm there. Here would be the elbow joint. There's the force H on the humerus. I'll call that point B. There's the tension of the bicep. Pulling back, it creates basically a lever kind of here. And there's 8 pounds pulling that way. Even though the person is pulling 8 pounds this way, what the arm feels is 8 pounds that way, Newton's third law. All right, so what do we do? Well, again, whenever we get stuck, we want to sum forces, we want to sum moments. We've been talking lately about summing moments being the key that opens up summing forces, because we have 2 unknowns right now, so we need at least 2 equations. We don't have anything happening in the y direction, so really this is just going to be summing forces in the x and summing moments. So let's start out here with summing moments. We're going to do counterclockwise is positive. I'm going to sum moments about point B. That's kind of the elbow joint. We can treat that as a pin. It allows rotation, so there's no moment set up, but it does prevent translation, so there'll be a force in the x and the y. All right, so what am I going to have here? If we have positive counterclockwise, that means I'm going to have a minus 8 times the 13 plus 1.75. That's the total distance from the 8 down to B. Okay. And then I'm going to have the force of the, or tension to bicep, that's acting at 1.75 up. 1.75 up from that, and if I set that equal to 0, I will get tension B. I didn't figure this out yet. I want to say it's somewhere around, that's around 14, almost 15. Let's see if we can do this quick on a phone. I'm going to pause it and get a calculator so we can find this out. All right, so if we go through that, it comes out to be about 64 or 67.4 pounds. And that's what you sort of feel in the elbow joint if you're doing that kind of exercise. We can then use that to do sum of forces in the x direction. Positive will be to the right. We don't worry about the y direction. There's nothing happening there. So I will have 8 minus that tension in the bicep, which I just found, plus the force H in the humerus has to equal 0, and that comes out to be force of H equals, what's that, tension minus 8, so that's minus 8, that becomes 59.4 pounds. Okay? 59.4 pounds. And that's basically a pivot there. And, you know, obviously, if it's sort of moment this way equals moment that way, since this is at a shorter distance, that has to be a much stronger force versus an 8 at a further distance. It's really counter versus clockwise, and that works out there. All right, so that's a quick problem there. Again, summing forces, sum moments. We typically look at summing moments first to clear that up. All right, let's go to problem 2. I'm going to pause it, clean off the glass, and we'll go from there. Okay, we're back. We have a third problem here. We're going to have a wrench The wrench is used to tighten the bolt at A, at the origin there. If the force of 6 pounds is applied to the handle as shown, which is 30 degrees above the negative axes, determine the magnitude of the resultant force and moment that the bolt head exerts on the wrench. The force F is in parallel to the XZ plane. So when I ask for the magnitude of the resultant force and moment that the bolt head exerts on the wrench, really what we're finding is the support reactions at A. And since that is a bolt there, we're going to look at X, Y, and Z for forces. We'll look about the X, Y, and Z for moments. Okay? Now, an older way of doing this would be to, let's just switch this up here, would be to R cross F this force. That would give us the moment in I, J, and K, and that would sort of answer our moments about the X, Y, and Z. So that's one option of doing that. It doesn't really give it what we're doing in the X direction, although we can sort of build that force into X, Y, and Z, and that would give us that. So that's a little different solution than what they would normally do by summing forces and all that. But let's try that, okay? Quick little free body diagram. So 14 inches, and there's I think that's actually above. There's the Y. There's 2 inches. And we have the force that is going to be in the same direction as the X. And that's going to be 6 pounds at an angle of 30 degrees. So that's going to try to cause some rotation this way. If that's the positive Z, positive would be this way, so that's actually in the negative Z direction. But that is trying to tighten the bolt. Okay, so if you look down from the top, that'd be a righty-tighty. So let's go through and see if we can put this force and put it in Cartesian vector form. If you remember that, that's going to be I, J, and K. In I, J, and K. So let's see if we can build that. That's going to be 6 cosine of 30 in the I. That's going to be 0 in the J because everything is lined up with the x-axis. And that's going to be a negative 6 sine 30 in the K. If I go through and do that, sine of that, 6 times 0.86, 6 times 0.866 is basically 5.20, and that'll be negative 3, and that is in pounds. Okay. Now, since that's the only force acting here, when I sum forces in the X direction, Y direction, Z direction, what's happening here at the bolt, which is going to give me an AX, AY, and AZ, they have to oppose and be equal and opposite to those. Equal and opposite to those. So just pulling these numbers out, I can get that AX is going to equal 5.2 pounds, but it's going to be this direction, right? Sort of the negative direction has to be opposite that. There'll be no component in the Y direction. There's nothing this way in the Y. And in the Z direction, it has to oppose this negative 3. Negative 3 is this way. That means I have to have 3 pounds, and that would be up. And that's a pretty easy way to get those answers if there's no other forces acting on there. Now, I could just say some forces in the X, and I'd have AX plus this 6 blah, blah, blah equals 0, and I get that answer. So this is just an alternative way of doing it. Let's see if we can do the same thing if we do it with the moment. If we find the moment at A, and we do that as R cross F, that's the 6, and we're crossing that with going from, and let's call that point B maybe. That's going from A to B. See if we can build this right off the bat here. I, J, and K. Position vector is going to go from coordinate A, which is 0, 0, 0, and that's going to go to coordinate B, which is what, 0, 0, 0, 2, right? I believe. So I'm going to have 0, 0, 2 here. That's the position vector, and the force vector here, if I can build that, and the x direction is going to be 6 cosine of 30. There's a 0 and 6 sine of 30. Again, I'm just going R crossing into F. That'll give us the moment straight off there. If I go through and get the moments, the moment at A, let's see if I have those numbers real quick here. That should give me 42. A little over 10, 10.4, and 73. And that's going to be inch pounds. Now that gives us the moment in IJK in Cartesian vector form as a three-dimensional vector. If we're looking for the moment individually in each of those, we just set it equal to each of those. So that's going to be the moment A at the X, the moment A at the Y, and the moment at A about the Z. Okay? Now, that doesn't give us the actual magnitude of the moment that's acting there, but we know that if we take the square root of the squares, that will give us the magnitude of that moment at A if we need to find it. And I think the question originally asked for the magnitude, but this gives us the support reactions at that point A, at the bolt. And if we want to know the magnitude, we square the squared. If we know the magnitude here, we do the same thing. And then we can also find that. And that would come out to be 6 because that's what that force is. So, all right, another one, something different. We haven't seen a wrench. Let's go to pause the screen and clean it off, and we'll be back to record another one. Okay, we're back with another example. Again, these are just great practice questions for the exam. As I'm sure I've said in class or lectures before, the only way to get good at this is to do problems. You just have to keep doing problems and recognizing that the way the problem looks doesn't change our approach. We always do a free body diagram. We always sum forces, sum moments. That's the whole semester, right? The only other parts are if we see forces in a different way, we have to build the forces, but we do sum forces, sum moments. So force yourself to practice when you get ready for an exam. Cover up the solution. Force yourself to at least start the problem so you know how to start it, and then the math will fall in later, okay? So here we have a truss. We have it's pinned over here at A. We're told that there's a roller happening at B that's at some angle. Okay, that's a 45. Write that as small as I can. 45 in there, and so we're told to find out, determine the horizontal and vertical components of the reaction at the pin A and roller B required to support the truss, set F equal to 600. All right, so there's our problem. I've made a free body diagram, or at least I've started a free body diagram by showing the 3 loading. I've showed the roller at the angle here at B, and we have a pin at A. A pin at A. And at this point, we want to go ahead and draw in our reactions or support reactions at A and B. Now, since it's a pin, it's going to have components in both the X and Y direction. We may want to look at that and say, okay, do we need a certain direction to it? Well, I'm expecting if this would pivot, it would pivot this way. So I expect that AX is going to try to be holding it back that direction. Okay. Also, I'm expecting maybe at this one would be up. I'm not sure. It could be down. All these are down. I don't know if it's helping. If it goes this way, it's more to helping it pivot. We can just pick AY as this because we're not sure of a direction. And again, as we've said before, if I pick the direction wrong, no worries. The answer comes out negative. I just switch the drawing and put it in the answer. No big deal. So I could always just pick positive A and X just to be able to start the solution. Now, what about B? Well, it's at an angle, but there's going to be a normal at B, so it's not really a BX and a BY. We'll just call it a normal at B. That way, it's only a single variable as opposed to an X and a Y that would have two more variables and give us 4 total, which we can't have in 2 dimensions. All right? So that's going to be at a 45-degree angle there, and we can solve that. All right, so here on, we just go ahead. Sum forces, sum moments. I'm going to start out by summing moments counterclockwise because that usually unlocks the X and the Y. And where do we want to pick? Well, I could pick B, it gets rid of B, or I could pick A, it gets rid of A. It really doesn't matter. Let's pick A up there because it does drop out 2 at the same time. So I'm going to take the moments at A. That's going to give me a 600 acting at the total distance across, which is what? This is a 2, a 2, and a 2. So that's 600 times 6, plus a 600 times a 4, and the other one is a 600 times a 2. That takes care of the 3 loading. Now we have the normal at B. We have to put it into the horizontal direction. So that's going to be cosine 45, right? That gives us the X component there. And that's at that distance there of 2. If I check the drawing, that's also 2. And all that has to equal 0. If I go through, I'll get the normal at B. Comes out to be about 5092 newtons. Now, I would leave this in newtons and not switch it to kilonewtons only because all our original loading was in newtons. So we traditionally will follow that and put all our answers in the same units, unless it asks us for something different. All right, some moments I found out what's happening here. I just need to know what's happening at A. So I can go ahead and sum forces in the X direction equal to 0. I'm going to get AX. AX is going to be minus, AX will be minus the B normal or the normal at B. NB, BN doesn't matter. And that's cosine of 45. That's going to equal 0. That gives me an AX equal, if I take 5092 times cosine of 45, that gives me 3600 newtons. And then if I just go ahead and finish this off by summing in the Y direction equal to 0, I'm going to get a Y up plus the normal at B sine of 45. That's also up equals 0. So I'm going to get a Y. Wait, I'm missing. Hang on, that didn't sound right. AY up and B up. Oh, I get all the minus 600s. Forgot those. That's huge. That will equal 0. That gives me an AY, if I go through that, of 590 equals sine of that, gives me 1800 newtons. And that also comes out to be negative, so I have to change that to 1800 newtons, and that's going to be down. Because the answer was negative, I'm going to change it. It doesn't seem intuitive by looking at that, but this is more, instead of pulling this away from, it's actually pushing down, because these are trying to spin it this way. And this is the one a little bit that's trying to, the combination of these two. sort of gives me a result. And this way, it's trying to spin it clockwise. Okay. All right, so that's another good one there. I think I have one more for you, so let's pause it again, and we'll erase the board, and we'll be back in a moment and give you, I think, one more. Okay, we're back with our last problem here on Chapter 5, just some additional problems to work through. We have a beam that has a distributed loading over the length of 7 meters. It looks like it starts at 200 for 4 meters and then ramps up from 200 to 400 at the end above B. We have it pinned at A. Roller B, again, is just simply supported. Again, the roller allows any kind of elongation so it doesn't buckle or have any stress in it, based horizontally and pinned at A. All right, so how do we approach this problem? Distributed loading, we haven't seen that in a few lectures, but if you remember, we want to break that up into common shapes if we can, unless we can integrate it. I'm seeing some common shapes here. One is a big rectangle, and 2 is a triangle right there. So to find that resultant force of those, I need to find the area of that rectangle. Length times width is going to give me 200 newtons per meter times a distance of 7 meters. Gives me 1,400 newtons, right? Just check the units there. That is the resultant force of that loading all the way across. So if I redraw this, there's the pin, there's the roller. I'm going to put that 1,400 and I'm going to put it halfway across. So I'm going to put that at 3.5. And I have 1,400 newtons right there. Again, I treat that as a point load now. It's coming from the distributed. If I go and find the area of that triangle, that's half the base times height. That's going to be half the base, which is over 3. The height is going to be, now careful, we have to use that height. It's not the whole height. We just use the height of the triangle. So that's 200 Newton meters, and that comes out to be 300 newtons for that. And that 300 newtons is going to be 1/3. It's always 1/3 in from the right angle. So I'm going to have 1/3 in, so that's going to be at 1 meter. This one's at 3.5. That's at 1 meter. This is going to be 300 newtons. And what I've just done is replace the distributed loading with 2 point loads that have the equivalent of that distributed loading and shows it acting at the centroid of those 2 areas. Now, obviously, I'm still missing some parts of this. I'm still missing the support reactions. So let's put an AY in here, and we'll put an AX, and then we also have a BY at the roller. And I could call this normal at B. Some of the times the book calls it normal B versus BY. Normal at B implies that it's vertical, it's perpendicular to the surface, but that works for us right there. All right, so where do we go now? Well, nothing new. Our approach, now that we have the free body diagram, is to sum forces, sum moments. Again, I'm going to start out by summing moments. I'm going to pick point A, just because usually starting at the left end drops out the pin right away. It drops out AX and AY. So I'm going to have minus 1,400 acting at 3.5. It's going that way. I'm going to have minus 300 acting at total of 7 minus 1, that's 6 meters. And then I have countering it, I have BY acting also at 7 meters. That all has to equal 0. If I go through that, BY is going to come out to be 957 newtons. 957 newtons. And that came out, let me get a different marker. That's the one starting to I think tank on me here. Trying to find the cap. All right, so that gets me a normal at B. What else do I have to find here? Well, I have to find the reactions at A. So I can sum forces in the x direction equal to 0, positive to the right. I'm going to get AX equals 0. No surprise, these beams are set up to handle vertical loading, not horizontal. Even though it's 0 there, doesn't mean we get rid of it. We still keep it pinned in case things would change. And then I finish up this problem by summing forces in the y direction, positive up. I will have AY minus 1400 minus 300 plus the normal at B, the 957, that has to equal 0. If I go through that mess, that's 1700 minus the 9, so that's 43, what's 743 newtons. It's positive, so the direction I picked is appropriate. And that's what we have. So let's do a quick check of this. I have 1700 newtons down. We have to hold 17 up, otherwise this is going to translate down. It will not be in equilibrium. So by the combination of these two, AY and BY, the combination of these two should equal 1700. If I add those two together, I do get 1700. That makes me feel good about that answer. And because it's the pin, there's no moment set up. And that's the solution. And those should be some good practice problems for review of Chapter 5 material. Again, our process does not change no matter what the drawing or the object or the image or structure we're assessing or analyzing. We want to draw a free body diagram. From there, some forces, some moments, or some moments, some forces. Doesn't really matter. Sometimes moment unlocks it first, but it doesn't matter. Whatever works for you, stick with it. But it's the same process. You should never have no way of approaching a problem like this because we know after some forces, some moments. Okay? All right, so that finishes up Chapter 5. As always, shoot me an email. If you have any questions on these, make sure you watch this. Again, cover the solution and force yourself to redo or at least start this problem. You don't have to finish it all the way to the math to the end, but at least start these problems so you know how to start them. And that's the tough part on exams, is knowing where to start. But again, free body diagrams, some forces, some moments, and you're good to go. All right, until next time, have a great day. Go Pens.